Hello and welcome to this video. In today's lecture, we will study the exercises 7, 8, 9 and 10 from the chapter 3 of the book Contemporary Abstract Algebra 10th edition by Joseph A. Gallian. Okay, we start with the exercise 7. The statement of exercise 7 is, without actually computing the orders, explain why the two elements in each of the following pairs of elements from the group Z30, which is group under addition modulo 30, must have the same order, and the order pairs, the two elements are 2 and 28 and 8 and 22. Do the same for the following pairs of element from unitary group under multiplication modulo 15, and here also the pairs of elements are 2, 8 and 7, 13. So we start the solution. We know that in Z30 the additive inverse of 2 is 28, that is 2 plus 28 is congruent to 0 mod 30, and therefore the inverse of 2 is 28 and the inverse of 28 is 2, and we know that the element and its inverse have the same order. So this means the order of 2 is equal to order of 28. Similarly, the inverse of additive inverse under modulo 30, the inverse of 8 is 22, because the sum of 8 and 22 is congruent to 0 mod 30, because 8 plus 22 is congruent to 0 mod 30. Therefore, we know that the element and its inverse has the same order, so order of 8 is equal to order of 22. Now we consider the second part in the unitary group U15, which is group under multiplication modulo 15. We know that if we multiply 2 with 8, we will get 16, which is congruent to 1 mod 15. Therefore, 2 and 8 are inverse of each other, and we know that the inverse and the element and its inverse have the same order. This means order of 2 is equal to order of 8. And similarly, 7 and 13 are inverse of each other under multiplication modulo 15, because 7 into 13 is 91, which is congruent to 1 mod 15. This means the order of 7 is equal to order of 13. We move to the next question. Question number 8. In the group Z12, here we have group under addition modulo 12. Find the order of A, order of B and order of A plus B for each of the cases. There are 3 cases which are given, and also there is a question, do you see any relationship between the order of A, order of B and the order of their sum? We start the solution. Case 1, when A is equal to 6 and B is equal to 2. Clearly, if we add 6 twice, we will get congruent to 0. Therefore, the order of A, which is actually equal to order of 6, is 2, because group is under addition modulo 12. So order mean we have to add repeatedly the elements until we will get anything congruent to 0. Okay. And similarly, order of B, which is actually order of 2, if we add 2 6 times, we will get 0. So order of 2 is 6. And similarly, A plus B, which is actually equal to 6 plus 2, which is 8. And the order of 8 is 3, because if we add 8 3 times, 8 plus 8 is 16, that will be congruent to 4 mod 12, and then once again if we add 8, we will get 12, which is congruent to 0 mod 12. So in the case 7, when a is equal to 3, by using the same arguments, we will get the order of a, which is actually order of 3, is 4, because if we add 3 4 times, we will get congruent to 0 mod 12, and order of b, which is actually 8, the order of b is equal to 3, and similarly a plus b, which is actually 11. If we add 11 12 times, we will get congruent to 0 mod 12. So the order of 11 is 12. Similarly, the case 3, when a is equal to 5 and b is equal to 4, then the order of a, which is order of 5, is 12, because if we add 5 12 times, we will get 60, and 60 is congruent to 0 mod 12. Next, order of b, which is actually order of 4, is equal to 3. And the order of a plus b, which is order of 9, if we add 9 4 times, we will get 36, and 36 is 0, congruent to 0 mod 12. So order of 9 is 4. And if we see everything, these three cases, we can see that actually the order of a plus b divides the least common multiple of order of a and order of b in all three cases. And this is the relation which we want to find. We move to the next question. Question number 9. The statement is, if a, b and c are group elements and the order of a is 6 and order of b is 7, then express this element without using negative exponent. We know that the meaning of order of an element is that is the least positive integer, such that if we take that integer as a power of that element, we will get the identity. So if we know that order of a is equal to 6, this means 8 raised power 6 is identity. And similarly, order of b is equal to 7, this means b raised power 7 is the identity element. Now consider 8 raised power 4, c raised power minus 2, b raised power 4, whole raised power minus 1, and by socks shoe property, we will get b raised power minus 4, c square, and 8 raised power minus 4. But we have to find the expression without negative exponent. For this, we know that b7 is equal to identity, and we can write it as b3 into b raised power 4 is identity. Now we have two elements whose product is identity, so it means they are inverse of each other. So b4 inverse is b cube. So this is b raised power minus 4 is equal to b cube. So instead of this b raised power minus 4, we will write b cube. C already has the positive exponent, so we will write it as it is. And now for a raised power minus 4, we will see, we know that a6 is equal to e, and we can write it as a2 into a4 is equal to e. And this means a4 inverse is equal to a2, because the product of these two elements is identity, so they are inverse of each other. And in this way, a raised power minus 4 is equal to a square. So instead of a raised power minus 4, we will write a square, and that is the expression, or that is the element without negative exponent, and that is what we want to show. The next question is question 10. Given that the group E, A square B, AB, A square B is a group where the order of A is 3 and the order of B is 2 and AB is equal to A square B, determine which of the 6 element is AB A square. We know that the group is closed under binary operation, so we have to find that what is this element. This element must be one of these 6 elements of the group. Okay. And also we have to find that this expression is another representation of one of the 6 elements of the group. Okay. We consider that order of A is equal to 3 and order of B is equal to 2. This implies that A cube is equal to E and B square is equal to E. Since B A is equal to A square B, and if we multiply this equation with A square, we will get A square B, and this is A square B A, and that will be A to raise power 4 B, but we know that the order of A is 3, so it will be AB, and that is A square B A. Okay. And if we post multiply with A square, that will be, and now this A and A square will be A cube, and we know that A cube is identity, so this is A square B, which is equal to A B A square. So the element, this element is actually A square B. Okay. Now the other element is A square B A B. We considered it, and we can write it as A square B A into B, and we know that B A is equal to A square B. So this is A square. Instead of this B A, we can write A square B into B, and that is A to raise power 4, or we can first remove this brackets, and now we can write it A to raise power 4 and B square, and we know that B square is actually identity and A cube is identity, so this will be A cube B square, which is equal to A into identity, and that will be A. So this element is actually another representation of this element. So that's all about today's lecture. See you next time.